In the first exercise, we're asked to calculate a squared plus b squared and to store the result in C. Nothing has been specified in terms of data types. So this is not a C code yet, this is simply pseudocode. There is no data type specified. So right now we can just choose how much space we will reserve for each of these, A, B, and C. So in the solution, we simply decided to go with 4 bytes for A, 4 bytes for B, and for C as well. Or to simply interpret it as integers of 4 bytes in C. So how did we write this program? First, we reserved in the data section, we reserved memory for A, B, and C. So we reserved 1 word of memory for A, and we store the value 2 into this word. Then we reserve 1 word for B, and we store the value 3 into this word. And then we reserve 4 bytes of memory for C. Now note that we don't yet know what value C has to be because this depends on A and B. We don't know in advance before running the program what the value will be, so we just need to reserve empty space. With the space directive, you can reserve bytes of space without having to fill them in with a value, which you do have to do with the word command. So 1 word is 4 bytes, so this reserves 4 bytes. This also reserves 4 bytes, but then without filling in the value. And you can of course reserve more bytes if you would want to. Just this first part, this data section, you can already see this in action. So when I press assemble, my data section will be prepared. So my data section, you can see it's displayed right here. You can show the text section as well. This is the code of my program. This is where it's located. But right here, you can show the data section. That's the default. And it shows you the first field of the data section, the first word, the next word. And this you can see is the 2 and the 3 that I've written down here. So you can toggle hexadecimal values and regular values depending on what you need to see. So we can see a value 2 and this value 3 is stored at those addresses, at address 10010000. And at this address plus 4, we have the value 3. And then this would be the field C. Another nice thing you can do is you can show this screen with the labels. You can do this in settings normally, show labels window, and this shows you your defined labels and their values. So A has the value, and their addresses. So A has this address, B has this address, C has this address. So this can be useful. All right, so that's the data section. Now we prepared our program. Now we didn't specify here that you need to write, oh yeah, we did specify that you need a data section. My bad. Okay, so that's the data section part. Next, the actual calculations. So now we just have to calculate A squared plus B squared, store the result in C. These values are in memory, so the procedure will be load the values from memory, the input values from memory to registers, then do the calculations in the registers and store the result from the registers back to the memory of C. That's what's going to happen here. The LW instruction will load the value of A into T0, of B into T1. Now our values are ready in registers and we can start calculating. We use the multiply instruction both times to do multiplication with itself. So A times A stored in T0. So now T0 stores A squared. T1 will store B squared after this line of code. And then finally, we will add these together. And we will use T0 to store the result. So T0 after line 32 will contain A squared plus B squared. Now that we have the end result, the last thing we have to do is to store this end result back in memory. Now it's only living in the registers. We have to store it in memory. And we do that by using the SW instruction, store word instruction. We want to store T0 into C. So note that this is the first time we've seen this annoying syntax in which normally we have destination source, but right here it's source destination. They did this to have a sort of symmetry with load word. But store word is like one exception to the general rule where the first argument is your destination and the second one is your source. In this case, it's a little different. First argument, source register. Second argument, it depends. You can specify a label here or an address. If you do specify a label here, then you need to also give a temporary register, and this register will be used to resolve the address of this label. So load W, so LW and SW both have to resolve the addresses of this label. Both of them have to do it, but only LW, the nice thing about LW is that it loads a value into a register, so it will always overwrite the value of T0. So LW is allowed to use T0 as well to resolve the address of A. When we translate LW, it will be translated, so this is a pseudo instruction, it will be translated into two actual instructions, and in the first instruction, they will resolve the address of A, and they will use the register T0 or X5, they will use that for the address resolution. And then they will actually load this value from an F offset to the address. So if you had written this code with an LA instruction beforehand and then the LW, fine, because in fact, when we assemble it, the actual basic instructions that will be executed are actually the same. So Allen's LA instructions to load the address of A would also be converted to a program counter relative instruction in BASIC. So we'll go into this into more detail in the future. Not a big problem if you don't understand this translation. No problem. We will get into that in future sessions. But for now, just know that if you've written LA first to load the address of A, and then you wrote an LW like this with an address, it's exactly the same. And it's fine to do as well. And then for SW, we need to specify this temporary register. Why? Because, well, we cannot use T0 as an intermediate register to resolve the label. We can't do that because we need the value of T0, right? So that was it for this first simple exercise.